previous slides, decomposition, reconstruction, thresholding. Thresholding, either it may be a hard thresholding and soft thresholding. I'm not more interested about thresholding, but I will show you. This is the paper DL transactions. Soft thresholding and hard thresholding, I will provide with an example here. This is a signal. The coefficients below some value are forced to 0. That is hard thresholding. In soft thresholding, the coefficients below threshold are forced to 0. The coefficients above threshold are compressed. They are reduced in amplitude. They are compressed. The values of the concerned signal are compressed. This is a soft and hard thresholding. So this is how the block diagram used by most all denoising application. Whether it is ACG signal, whether it is a PPG signal, whatever other signals, EOG, any signal you may use this procedure. You choose a mother wavelet, that is very important. Level of decomposition is another important. How you choose the level of decomposition is frequency of interest. Where the frequency of interest? Suppose I am interested in D7 frequency components 0.48 to 0.97. Then you perform up to 7 level decomposition only. You cannot go for 11 level. But in this application, what I have done here, I require the frequency component 0 to 0.03 Hz. That's why I have gone up to the 11 level decomposition. I have gone up to the 11 level decomposition. So that gives the level of thresholding, and mother wavelet decides the thing. Thresholding are there, soft thresholding and hard thresholding, all those are there. You can choose anything. So this is the best example I will provide to you. First one is a signal, yes. If I consider only A3 component, approximate 3 component, 3 level decomposition has done. This is a signal waveform. Only D3 coefficient. Okay? I have considered only D3 coefficient and reconstructed the signal back. So this is the signal. D2, D1. I will show you the example. Even I will open the MATLAB and I will show you the same example to you also. Same example, one more example. Changing its frequencies with reference to time. Yes, A5, D5, D4, D3, D2, D1. There's a chirp signal I have considered in the first few slides. 2 examples. So we'll see this program. So see here, load, don't worry about this command. Inbuilt some signal is there. I have used the same signal. So I'm loading it to a variable S and wave DEC S signal, 5 level decomposition using simplet wavelet. Sim4 is the 4 simplet wavelet. And next, reconstruction, WRCOEF, using only approximate coefficients of this matrix C and L. I am reconstructing the signal only using the approximate coefficient. That is, only A5 will be there, so A5. And one more example, if I consider D, means considering detailed coefficients. Detailed coefficients I am considering 2. 2 means D2. I am considering only D2. So these 3 operations has done, and same 3 waveforms I have shown here. Plot 3, 1, L, plot S, plot A5, plot D2. I will show it to you in the MATLAB. Same example I have considered here. Yes. Same example. Yes. So same program I have shown to you, load sums in and all these operations I have shown now. So I'm constructing A5 signal with considering only A5 coefficient. I'm constructing D2 signal with the D2 coefficients only. That is shown in 311, 312, 313. Just a given title, this is a decoration, nothing more than that. So I'm running the program. Through this application, it may not run, I think, but I have copied down the same answer results of that waveform and I'll show it to you. With this application, I think it's not running. This is outputs. This is outputs. So this is some central signal. This is A5. This is D2. You can decompose the signal of your interest. Position or 6-level decomposition. So I used only two commands here. Wave DEC WRCOAF. You can see in the MATLAB space type help space wave DEC and you can read the information. It is same thing I have provided here with equations with the complete block diagram. I have shown you here, that is wavelet decomposition, how it looks like, how C and L matrices will be provided. So I have taken an example also, one more example, I'll show it to you. This is example. Now I want to do example, see here. Now see here. I want to do a 6-level decomposition. So C matrix consists of A6, D6, D5, D4, D3, D2, D1. In MATLAB, this is additionally provided. Length of the total signal which is done decomposition is provided in the last. It is provided in the last. It is L is equal to length of A6, length of D6. So L is length of individual coefficients presented in the C matrix. So length of A6, length of D6, and last one is the length of signal. So I want to do a 6-level decomposition. This is how C and L matrices will be looks like. This is how C and L matrices will be looks like. So see here, how I'm doing a different interesting parameter here. See here, zeroing unwanted components. I'm thinking that it's unwanted component. Example here, I've considered a simple PPG signal. This is part of the program I copied down here. I've considered a PPG signal with a DB10 wavelet, actually 6-level decomposition, as mentioned previously. 6-level decomposition. So I want to make L2, nothing but this is L matrix. Length of A6 is first element of the L matrix. Length of D6 is second element of the L matrix. So I am considering here L of 2. L of 2 means the L matrix. 2 means second element is length of D6. So I am forcing all D6 elements to 0. I am modifying C matrix. I am modifying this C matrix that I am forcing D6 components to 0. D6 corresponds to which frequency component? You can take a simple paper and pen. You do with the sampling frequency. You will get what is the D6 frequency components. So how I am using that? See here. C already done C matrix. C matrix I am modifying, forcing some values to 0. It is L of 1 plus 1. That is L of 1 is nothing but length of A6. So I am not touching A6. Length of A6. Length of A6 say some value plus 1. So seen here length of 1 plus 1 colon length of 1 plus 2 is equal to zeros of 1 comma L of 2 means I am forcing the D6 coefficients to 0. I will give a simple example here. Suppose length of A6 is, suppose the first element of L is say 36. Length of D6 say 20. So 36 means in C matrix first 36 elements are corresponds to A6. That is A6 length of A6, that is L first element is 36. So C matrix first 36 members or elements are corresponds to A6. Next length of D6 is the second element of L matrix. Length of D6 is say 20 means next to 20 elements are corresponds to D6. Next 20 elements are correspond to D6. Now I want to make D6 elements 0. So I have written the program here that 36 plus 1 means 37 to 36 plus 20, 56. So 37 to 56 all elements are corresponds to D6. I am forcing them to 0. I am forcing them to 0. This is how you can zero the unwanted components. This is a MATLAB program written by me here. Can force the concerned values to 0. Now, see here the last line. I am forcing length of 4. This is 1, 2, 3, 4. 4 means D4. I am forcing all D4 elements to 0. I'm forcing all D4 elements to 0. So I'm writing here C of, this is forcing, see, you can force the values of a certain matrix to any value. I have a C matrix, suppose 1 by 100. I will modify 1 to 10 elements. You can modify. I will modify last 10 values. You can modify. You can do it in MATLAB. That's how this step works. I'm modifying certain elements. This colon nothing but incremental by 1. This colon incremental by 1. That is 37, 38, 39 up to 56. Up to 56. So 37 to 56 elements are forced to 0 in this case. See the last case. It is C of L of 1 plus L of 2 plus L of 3 plus 1 to L of 1 plus L of 2 plus L of 3 plus L of 4 is equal to zeros of 1 comma L4. This command means it creates a matrix with all elements 0. The size of the matrix is 1 by L of 4. That is how you can zero the elements. You can zero the elements. Whichever the coefficients you don't require, you can do modifications to that signal. So this is another example where I can do directly. So I have actually a noisy ECG signal with me. I have performed a wavelet decomposition, 10 level wavelet decomposition using a DB10 Debachis wavelet, in-grid Debachis, the pattern Debachis wavelet. Now A10 I am constructing here with WRCOEF, a approximate matrix. So only using approximate coefficients, A10 will be constructed. D10 with considering only D10 coefficients only. Likewise, you can write the program and you can see the result. Same thing actually I have seen, but with this using our previous results are provided here. Previous results are there. Previous MATLAB result you can see here. Now I will show you again this program to you, which is there in ECG wavelet array, as you can see. So. So noisy ECG signal I have considered, 10 level decomposition I have performed, and I have used a different, same thing, what I have provided, what I have taken in this slide is there in this MATLAB, and it's taking some time because I'm using with this app. So it's, MATLAB is taking some time to run this program. Mostly I'll press run, we'll see the result after 1 or 2 minutes, I think. So otherwise, however, I say you're getting the result. You're getting the result. So I will show you the waveform exactly what. This is the waveform I have considered for decomposition. This is the waveform I have considered for decomposition. Then I got the result. The decomposition result you can see here. This is decomposition results. You can see all these results are decomposition. So the program is WRCOEF A. For A, number is not required. From D onwards, you have to mention the last value 10, 9, 8. Whichever coefficient you want, you have to mention the concerned point here. So same result, even I have copied in the slides also. You can see that this is the two signals I used for decomposition, and this is how the result you got from the decomposition structure with considering individual approximate and detailed coefficients. Otherwise, instead of doing this wavelet reconstruction command, I already provided that zeroing that coefficients, you can do that also. So that you can zero the concerned frequency components and you make it other components as it is. So this is a decomposition structure and the decomposition levels of that ECG signal corrupted with the signal. So same is provided here again. So this is the MATLAB program. So one more example is there with me with the wavelet decomposition considering a PPG signal. I will show you exactly the thing required here. So see here. So wavelet decomposition, 6-level decomposition with the WG's wavelet DEC 10. I'm forcing some values to 0 and I will see the result here. So you can see here. You'll see the result concerned corresponding to the different coefficients. I am zeroing some coefficients. So I got, this is the original signal. This is, I made some of the coefficients 0. This is the signal I got as an output. Actually, that is not part of our work, but I am showing just how I am making the values 0, the same thing I have provided in the previous slides. So this is how you can decompose the signal of interest into different scales and you modify the approximate and detailed coefficients. You can modify the approximate and detailed coefficients, whichever you want, you approximate, detail and modify based on the thresholding also. So you can see here, you can see here, help wave DEC. You can see this wave DEC performs 1D wavelet decomposition, gives a C matrix, L matrix. Everything is provided here, C, L and all. And next, one more is there missed here, which is a beautiful command. It is, see, denoising steps I have provided in the block diagram. It is decomposition, thresholding, reconstruction. These three put together into a one function in the MATLAB. That is, I will show it to you. That function is also, it is helper. WDEN. This is the command used for wavelet denoising. Wavelet denoising. You can see here, X is the input, TPTR is the threshold, SORH is a soft threshold or hard threshold. Scale, some value which is provided there, either 0 or 1, generally provided. N is the level of decomposition. W name is window name. You'll get the directly output XD, the denoised signal. This is the command you can directly use for denoising of your signal. That is, it performs decomposition, thresholding, and reconstruction. All these three steps combined into a single one. That is, X is the input, TPTR is a threshold, SORH is the either soft thresholding or hard thresholding. You can mention directly S or H. And scaling, generally no scaling will be used one, and level of decomposition and window name. I have used the same thing in one of our program. I'll show it to you that also. Yes, you can see here. You can see here. WDEN, ECG noisy lead 1. SQT WO log is the thresholding formula. This is provided here. SQT WO log is universal threshold. That is square root of 2 stars. Some formula is there. If you read the complete information, you may get that exact information. SQT WO log is a universal threshold formula. Otherwise, you can use a Ring-Schur heuristic, any one. Right. Then, so S soft thresholding, SLN scaling, 10 level decomposition, and EP10. And ECG underscore HK, I have plotted in the waveform 9th. So I'll run the program and I'll see the result, 9th one. This is to eliminate the power line interference from ECG signal. I have done this work. This is the output. This from ECG signals have been, you can see actually the power line noise signal also. You can see that, yes. This is power line corrupted signal. This is power line corrupted signal. With using wavelet denoising, we have eliminated. You can see a smooth signal without noise. You can see this. So this is wavelet denoising command. Using wavelet WDEN command, you can directly eliminate the noise. But instead of using the direct command, you go for wavelet decomposition, reconstruction, sorry, thresholding and reconstruction. And same wavelet based approach, this decomposition tree is used for actually compression. Compression, nothing but I think all you know what is the need for compression. I no need to explain what do you mean by compression. So we'll eliminate the redundant data and we'll transmit the remaining data, but which represents the original information. So for compression also wavelet transform is used for either signal compression and image compression standards. Wavelet transform has been used. The procedure is similar. That is a decomposition. If you want, you can apply threshold. Otherwise, you can eliminate. After decomposition, the decomposed coefficients will be compressed by means of different encoding mechanisms. Run length encoding, Huffman encoding, or different mechanisms are there. So that coefficients will be transmitted to the by the transmitter. At the receiver, the inverse operation of run length coding will be done, and inverse operation of wavelet decomposition, that is wavelet reconstruction, will be done. Wavelet reconstruction will be done. So that's all for my today's lecture. So mostly I have concentrated the wavelet on the wavelet perspectives on decomposition and reconstruction. So if anyone have any questions, please feel free to ask me to queries related to this wavelet transform.